So let's continue. I'd like to show you this particular, how the layout has been done. So I want to focus your attention here. So here it is 43. These are all constant. These are the decisions. And solver will compute for this area. Solver will minimize this. This is called minimization because it is now the total cost. And these are constant. This is given from the problem. Now, how are these formed? This is, you see, some product B4 to C5. If I press F2, you see here, this is this, B4 to C5, and B10 to C11. All right? So this is the first formula you have to take. This is what we call objective function. I'll say here formulation, meaning you have to formulate the formula. That's one. And then secondly, here, it is just adding this together out from the factory. So this is B10 to C10, and here it is B11 to C11. And look up there. Okay. Also down below, if you look at this, it is B10 to B11, B10 to B11. All right, and also here C10 to C11. That's it. So you have here the what I call the issuances formulation. So factory 1 issues, issuances formulation. And you see these ones, this part here are the deliveries. Where should I write it down? Let me write it down here so it doesn't cluttered. Deliveries formulation. Okay. So this okay, those are the deliveries. Deliveries formulation, this one, and the issuances. Now the issuances formulation, sometimes it is equal or sometimes less than equal. It cannot be more than what you're capable of delivering. So in this particular exercise, we use equal sign. So here equal sign. So the issuances should be equal to the supply, and the deliveries should be equal to the ordered here. You do not deliver more than what are demanded. So let's now formulate the objective function. We go now to data, and then the solver here. You see it? I'm going to clear everything, reset all. I press reset all here. Okay. Now, I'll say for the objective function, I'll go to the minimization here. So press OK here, there. So I have minimized it, and I'll say minimize. And this is the decision variable. Whatever, when they say changing variable cell, that's the decision areas. And then we have here the constraints now. You can just say like this, add, make this, anyway they are all equal. So equal to this. Okay, so you now have here uh, F14, and then minimize the formulation, changing the variable cell, this one, and then we have here the issuances, and then we have another one, the deliveries. The delivery should be equal to the ordered, so you add now. What are the deliveries? These are the deliveries. 4 and 2 is equal to the constraints. These are the constraints. So let's check. Double check. So we have here E10, E10, E11 is equal to G10. All right, G11, and then this is B13, C13 is equal to B15 and C15. That's right. And make unconstrained variables non-negative. Check it. Checking it means you want the variables, those things which are not mentioned, to be positive all the time. Because there are cases when you want them negative. But in this case, we want everything. In business, we want all numbers to be positive or zero. And then we have here selecting a solving method. Is, you see, it's, for our case, we always use simplex LP. There are special situations, which the next discussion I'll show you. But that is not like being used all the time. In logistics, we are using this transportation problem most of the time. Okay, so I'll just solve it now. You look what will happen here, because these are just my guess. And then look at this. Then I have a solution now. You see, the total cost minimum 13,500. I'm able to satisfy the requirement. You look here first. Factory 1 and Factory 2 is capable of supplying 100 and 200, and I am issuing from these factories 100 and 200. Okay, that's good. And into the customer, the deliveries to the customer, 150, 150, 150, 150. And this is the cost, which you don't change this. And this now my decision. From Factory 1, I do not deliver to customer 1, but from Factory 1, you deliver 100 to customer 2. Then you satisfy it. From Factory 2, you deliver to customer 1, 150, and to customer 2, 50. So in total, the requirement of customer 2 is satisfied by Factory 1 and Factory 2. And customer 1 is satisfied fully or wholly by Factory 2. So the answer is this. All right? And we shall now go to the special application of another problem for the use. This we really reuse this. This is actually problem 1 of your exercise. Let me just discuss it. The problem statement is you are the owner of a small factory with a fixed client base. So fixed client base means you don't have a lot of clients. So you just go fixed. You are planning on upgrading your facilities, a production line. You need to buy that equipment, 40,000, and you want to pay it in 12 installments. But the point here is that you would like to get to pay this in 12 months, and the cost of the machine, which here is 40,000, you want to allocate it to the customer. You want them to pay. This is a very good application for example, for the gym, where you have a fixed client base, and you buy a new equipment, but this equipment you will allocate the cost to the customer. How are you going to do that? Like, if you look at this particular example, you have the cost of the new equipment is 40,000. You have your client. In this case, he says the base price is 1, meaning in this particular formulation, he says, I have 50, so 40,000 divided by 50, and the base price is 1. Suppose I make the base price as 2. Let us look at this example. Suppose the base price is 2 here. 40,000, 52. So you multiply this together, 50 times 2, then you have 100. Then that's what you do. 40,000 divided by 100, you get 400. So in 400 months, if you do it that way, you will be allocating, you will be able to determine, you'll be able to allocate 100 for each client. 50 base price, okay? So you go to 3 like that. So the issue here is that how many times are you going to in what way are you going to make a decision so that you can pay in 12 months? So I made here a computation, like say for example you have 40,000. You have here 50 members, and you divide it by 50 members by 1. So in effect 1. So if you, for example, charge them 40,000, which is this amount divided by this amount. So in 800 months, so that means you are just paying 50. If this is 40,000 SR, so this is 50 SR per month. So you need 800 months. So you now change. You change your approach now. You want to increase this to 10, so that per month you are paying 500 SR per month. So you need this amount, 500 SR per month, 40,000. You have 80 months. In our case, we say, all right, I have a client base of 50, but I'm going to double to charge them. I'm going to multiply this by 66. That's the base price. 66. For 66 times 50, then I'll be able to pay in 12 months, because I will have 3,300 per month. All right. If you go back in this particular formulation, the 66 is the amount of money you collect from the client. You're asking money, 66 SR. 66 SR per member. So that this particular decision, this base price, is actually the contribution of one client. So at 66, you will be able to pay back. So this base price is actually contribution from each client. This is the contribution from each client. So if each client will be paying 66 per month, monthly contribution from each client. Monthly contribution from each client. All right. Then if one client will pay 66 times 50, I have 50 clients, then I will be able to have every month 33,000 3,300. I will have 3,300. So I have a total contribution. So like I will have here the monthly total contribution from client, from all client. So that will lead me to pay back the machine, in the following months. So in 12 months, I'll be able to pay. So this is what I'm going to collect from them, this 66. Okay. So now, given this particular understanding, let's now do the solver. In this particular solver, so I have here, I rewrote the equation. So this is the column, and this 26 is this, 26, 27, 28. So we don't get lost. So we minimize this. This is the fix. We are fixing this. We are fixing this, fixing it to 12. All right. So that's K12. Now let me show you again the solver K12. So this is yeah, and then that's 12. Value of, what is your decision area? The decision area is this, K27, 50, and up to 28. Although you make a decision to be K27, K28, we make the K27, the clients, to be 50, less than 50. And we make the machine to be equal 40. All right? And take note, make unconstrained the variables non-negative. And here, in terms of the select solving method, it's GRG non-linear. And so when you run this, you solve this, the answer is this 50 and 66, which this is my trial and error approach. So 50, you see here, 50, 66, and 50, 66.6, and this is 50.67. You get it? So I hope this is clear, and I hope this and this matches, that you can see this particular connection. I need to get some shapes. This project base, or this monthly total contributions from all clients, is not shown here. Delete that. Insert, and we have illustrations, shapes. This is the base price, huh? The monthly contribution, this one, monthly contribution from each client, and of course that's the client, and we have this. So this is a very important decision to make. All right. So I changed the variables, the cells, but essentially the approach is the same. I hope you learned something from here, and this is a very good application of LP in non-LP situations, because we are using here GRG nonlinear. In general, we always use this. I hope you understand this properly and very well. And so that's it. This ends the discussion on optimization. Bye.